Well, okay, now let's see what is this different types of logic styles. So we are going to look into few major logic styles under static CMOS. We would like to see the basic conventional static CMOS, ratioed and pass transistor. While it comes to dynamic, we are going to see domino and NP CMOS. Basically, let's see what is the difference between these two type of logic. In your earlier classes, you might have been familiar with some of the basic thing like you would have gone through resistor transistor logic, transistor logic, diode transistor logic, and you might have even compared those different types of logics with respect to power, timing, speed, all this. Very similar to this in CMOS also, you could come up with the different logic styles for implementing any Boolean function, and you can also go for comparing this different logic styles with their merits and demerits based upon the metrics like area, power, timing, all this. That's what we are going to do. The basic comparison like static and dynamic, all the static there is no clock. When I come to dynamic, it has a clock for performing or controlling this operation, right? When it comes to static CMOS, it's a very trivial one what we have seen earlier. So if any Boolean function is given, y equal to a plus b the whole bar, we try to implement that by using 2n number of transistors, where n represent number of input. Say it has two inputs a and b, so I require 4 number of transistors, wherein 2 will be the number of transistor for NMOS, another 2 for PMOS. So you could make a PMOS tree structure and NMOS tree structure, and thereby you could make a static CMOS. The beauty of this particular static CMOS is it's very systematic and you can very easily implement, right? Okay, and one more thing, the basic structure would be a PMOS tree would be connected at the top and the NMOS tree would be connected at the bottom. PMOS tree would be connected to VDD, NMOS tree would be connected to ground. The common point of both PMOS and NMOS would be taken as my output and the gate of both PMOS and NMOS, they would be taken as my input. This is how the typical structure will be there, and it is most robust structure and it doesn't require any clock, and at any point of time the output would be either be connected to VDD or connected to ground. At no point of time in a steady state you could see there, there will not be any direct path from VDD to ground. So that's the beauty of this, which means if there is no direct path from VDD to ground, then there is no power loss. So ideally there is no power loss in static CMOS, but we could again notice that during the transition period, though both the PMOS and NMOS would be in on for a fraction of a second, and that gives rise to the development of short circuit current, which again gives rise to a huge amount of short circuit power loss. So in turn you can implement any Boolean function using this basic idea, right? So it would be connected to VDD or the ground, and all the gates are going to be my input. So this is the typical structure which we have discussed right now. Let's see what are its beauty of this. It has a high noise margin. When you go for static CMOS implementation, it has a high noise margin, which means the output high and output low are VDD and ground. What do you mean by this? In this structure, what we have seen is the output is either being connected to VDD or being connected to ground. There is no other intermediate state between VDD and ground. This gives a full swing, like the output is either at 0 or at VDD. Thereby the difference between the on level and the off level. Since that is large, it gives a huge noise margin. Better the noise margin, then the system is most robust, and it is against the, or it has most amount of robustness towards the noise. Next, no static power consumption is being taking place in the static CMOS for the simple reason there is no direct path from VDD to ground at any point of time except the transition, which means under steady state mode there is no direct path. Since there is no direct path, current is 0, power is 0. And one more is it has an equal rise and fall time, which means the PMOS network and the NMOS network can be sized such that the rise time and the fall time of a output can be made equal, which means comparatively the rise and the fall of an output can be almost equal. This you can do it by appropriately sizing those PMOS network and NMOS network. The next comes the what you call it as the pass transistor. Yes, the previous logic, static CMOS logic, whatever we have seen is very good with respect to noise margin, stability, robustness. But one of the worst problem with static CMOS is it requires 2n number of transistors, which is actually more amount of area consuming, connectivity consuming, and thereby more amount of capacitance. All this will get attached towards it. So to somehow get rid of it, people start thinking about an alternate method. What you call it as the people come out with pass transistor logic. This pass transistor logic is typically simple. Like what happens is you can just use the MOS transistors as a switch, and thereby you can build up your network. So the idea there is whenever you keep two MOS transistors in series, it become in multiplication, and whenever if you put them in parallel, then it becomes in OR operation. Right. So one best way to get out of this static CMOS is people can go with the pass transistor. In fact, we will put a separate video on pass transistor, which has been discussed earlier. So the pass transistor itself, you can think about coming up with a pass transistor logic. Among all the logics which are available, pass transistor logic is the logic which consumes the minimum or the least number of transistors. Next, we will move on with ratioed logic. The name ratioed has come into picture for the reason the output is not merely going to be connected to VDD or to the ground, or the output is something like you are tapping the output or scaling down the output. Say for example, I have resistance R1 and R2, and this is my VDD. If I tap my output at this point, it is VDD. If I tap my output at this point, it's not VDD, it is R2 divided by R1 plus R2 into VDD. When I tap my output at this point, it is going to be count, which means the output is getting ratioed based upon the point where you are tapping your output. So when you come to this ratioed logic, it is the output gets scaled down. Whereas in the static CMOS logic, it is not so. What you could notice is the output either being pulled up or pulled down, which means a full swing is being available there. So to construct the ratioed logic, you can come up in three ways. Either you can go for resistive load. You can remove this PMOS completely, right, and replace that with the resistive network, or else you can even replace that with the NMOS, which is a depletion type MOSFET, or you can even replace that with the PMOS, which is permanently being connected with ground. So all these three styles of implementing a Boolean function could show you very clearly the number of transistors would have been drastically reduced from 2n to n plus 1, where this n indicate the number of transistors for pull down network, whereas this 1, even it could be 1 or even 0. If it is a resistive load, you can just directly have a resistance, or else you can use an active device as a resistance, like you can use a depletion load, or you can use a PMOS which is being permanently connected to ground. So at the maximum it consumes n plus 1 number of transistors. So when I go for ratioed logic, the number of transistor count get reduced, which means the area get reduced. Thereby I can use, wherever the area constraint prevails, I can think of using this ratioed logic. Right. In fact, this method was introduced keeping in mind to reduce the static CMOS transistor count to very low value. When you look at the past transistor logic, yes, of course it reduces the number of transistors, but the problem is it seriously faces the voltage drop. When I connect a couple of transistors in series, then what happens is there exists a voltage drop from one end to the other end. So thereby there is a problem of strong 0 and strong 1 transmission. To avoid that, people come up with this ratio logic. Okay, let's see the properties of this ratio logic. Definitely it is going to have n number of transistor plus load, and as far as output swing output high, output low is concerned, output high will be connected with the VDD, so definitely this will be equal to VDD. But when it comes to output low, it can't be exactly 0, because say something like this: I have one resistance and you have one NMOS. This has been connected with V in, and I am tapping my output here. So if you give n in equal to 1, this NMOS comes into on, and now I am tapping the voltage at this point, which means this resistance is there and this on resistance of NMOS is also there, right? So if I consider this to be R1, my output is not going to be 0, rather it is R1 divided by R1 plus R into VDD. That's what we call this as a ratio logic. That is pull down network divided by pull down plus load resistance. And also you can expect this, that's what you are going to have in output low. Asymmetric response, yes, because the as what we have seen in static CMOS, you might not be having equal rise and fall here, because the resistance what is being possessed here may not be same as pull down network, and definitely you will have a static power consumption. Why? Because if this NMOS comes into on, directly you are going to have a path from VDD to ground, so which will lead to the current flow and which will give rise to the power consumption, right? Static power consumption. And the third point is the propagation delay is 0.69 RLC. What is this? This is nothing but the propagation delay of a simple RC network. So this is my resistance and this is my capacitance. That's the propagation delay of this. So when I summarize this ratioed logic, of course it reduces the number of transistors, that's fine, but the noise margin also get reduced. And one more disadvantage, the static power consumption is going to be here, which was not in static CMOS logic. To remove or to reduce the power consumption, people came out with some other solution, replacing this load resistance by active devices itself, something like NMOS and PMOS, which are permanently on. So this will be permanently on, which is almost like a resistance. This PMOS which is being connected to 0 will also be permanently on, right? So based upon this input combination, it will either be pulled down to ground or it will be at 0. That's what. So that's what we call it as pseudo NMOS. Means having a PMOS at the pull-up network which is permanently on, we call it as a pseudo NMOS. This depletion type NMOSes, you have a MOSFET which is being permanently being on, where the gate and the drain is being shorted. Correct. Okay, so that's what we have seen. So output high will be equal to VDD. What about to quantify exactly what is this output low? You can just equate the current flow, and thereby you will end up this formula, wherein output low will be equal to VDD minus VT 1 minus Kp by Kn. Direct substitution. Okay, so that's what your output low, and of course you have a static power consumption, and based upon the width of the PMOS load, you can even see how the VTC changes, voltage transfer characteristics changes. In the earlier discussion, we have seen when VTC changes, it will again change the noise margin of that particular circuit. That's what happening here. Right. One more important point here is in pseudo NMOS, that's ratioed pseudo NMOS logic, what you could notice here is this is more suitable when the number of inputs are high. Means fan in, when the fan in are large, you can think about using this pseudo NMOS logic. And another one more point we would like to discuss here. In our earlier static CMOS discussion, if I want to implement, say, a Boolean function y equal to a plus b into c, something like this, some Boolean function, and you have been given a chance to implement that using NAND gate and NOR gate. So the choice would be, naturally, people would be selecting NAND in case if you are going with static CMOS. The reason behind that is, when you look at the NAND type of version, there your NMOS will be in series. Say suppose y equal to a dot b dot c the whole bar. Here what does that mean? Your NMOS is going to be in series, PMOS is going to be in parallel. Why do we say this? Now this 3 input NAND, I prefer to go with stacking NMOS in series. Why? Say let's do like this. Stacking an NMOS in series, stacking a PMOS in series, which will be preferable? Obviously, stacking an NMOS in series is preferable. Why? Because the NMOS speed is around 2.5 times or even 3 times higher than that of the PMOS. So if you stack an NMOS, so it's actually the series combination of all these 3 add up together to form the delay. So if you keep on stacking an NMOS, preferably that is better compared to that of a PMOS. Why? PMOS is already slow. If you keep on stacking that, still it drag down the speed of that complete system. So in general, if a chance is given to select or to implement a Boolean expression using NAND or a NOR, generally people prefer NAND gate implementation. But coming to pseudo NMOS type, here if a choice is being given to implement a Boolean function using NAND or NOR, we won't be preferring this NAND, rather we will be preferring this NOR. Now comes the question, why should we do like this? Because see, in the earlier static, the NAND was, in the NAND gate NMOS is in series, NOR gate PMOS is in series. So that's the reason we neglected that NOR. Coming to pseudo NMOS type, look at the pull-up network. It is just a single PMOS which is kept in node. So you need not bother about the pull-up network. When you come to pull-down network, it has only NMOS. Now the question is, having an NMOS in parallel or having an NMOS in series? That's where the question rises. If it is NOR implementation, you will be having NMOS in parallel. If it is NAND implementation, you will be having NMOS in series. Had if this would have been a static CMOS, you will be having 4 PMOS in series. Definitely we would have neglected this. Rather now it is just a single PMOS. So what happened is, I would like to prefer only the NOR because the maximum critical path is only one gate, one NMOS gate. Whereas you look at this in the NAND type, you have 4 which has been stacked one above the other. So definitely we will not prefer this. We will prefer NOR. So the answer is very simple. When it comes to ratioed or pseudo NMOS, we will be preferring NOR, whereas in a static we will be preferring NAND. Okay. The next come the DCVSL logic, that is dual cascade voltage switch logic. What is this, or what is the purpose of this? Basically, there are some circuits where you require both the signal and its complement being available at the same time. But what generally people do, you can get your output and then pass it on through an inverter and then take the output complement. Yes, that's a good idea, but the problem is the time delay between output and output bar. If you look at, there will be a time delay of this inverter. For a high speed network, you could see there exists a timing difference between these two networks. So people thought you need to have some sort of network where you can have the output and the output bar to be available at the same instant of time. With that idea, you come up with what you call it as dual cascade voltage switch logic. And one more beauty of this is you can optimize this circuit so as to reduce the number of transistors to nearly half of it. And since you reduce this, the wiring reduces and you get the benefit of having output and output complement. In that way, it is it is being appreciated a lot. And one more with respect to switching activity also, this has a minimal switching activity compared to that of the other static CMOS. So dual cascade voltage switch logic. So that's what. So it's used to implement the complex functions where you need a signal and its complement. By going for this logic, the number of gates get reduced by 50%. That's the beauty of this. And in fact, the time also get increased. The speed of the network get increased. All this are again an added advantage of this. But one point is here, when it comes to DCVSL logic, the number of wirings that required almost get double. That routing that is going to take place, and the transistor counts also get increased. So with all this compromises, still for implementing some of the complex network, this DCVSL logic is good enough. Say this is for XOR and XNOR, you can functionally verify them also. So by giving different value of A and B, you could get XOR and XNOR function. But individually, if you start implementing XOR XNOR gate, definitely you could see the number of transistor count will be really high. And also you could see you do get rail to rail swing, not like a ratioed logic. The output is either at VDD or to the ground. So you have a full swing, right? And one more thing, there is no static power loss in this DCVSL logic. Since there is no direct path, you can completely avoid the static power loss. The next and most important type of logic style is dynamic logic style. Coming to dynamic logic style, this logic style will be using clock. Means I am trying to regulate, I am trying to come up with a solution wherein there shouldn't be a static power loss, but at the same time I need to have minimum number of transistor and a controlled operation need to be there. Keeping all this in view, we come up with one different logic style, what you call it as the dynamic logic style. Here the number of transistor required is n plus 2. N is for number of transistor for pull down network, and two transistors are for clock, right? One at the top, what you call it as a header, the other one at the bottom, what you call it as a footer, right? Yes. Now you can build up this network using pull down or pull up, so you can follow either of that. So that's what, if it is a pull down, you will be taking your output at the top. It's if pull up, you need to take it at the bottom, right? So you will be constructing this with the PMOS, this with the NMOS, this is with the NMOS, this is with PMOS. Both the versions are possible. This is N network, this is P network. One more, this works with the clock. As we said, it is going to work with a common clock, but the point to be noted here is it is going to work in two different phases, what you call it as a pre-charge and evaluation phase. What do you mean by pre-charge? Pre-charge is nothing but making the clock equal to 0. If you make clock equal to 0, what is going to happen? The PMOS comes into on and it charges the output node capacitance to VDD. That's what we call it as a pre-charge, right? Pre-charge means by default, irrespective of what is there in my input combination, my output is going to get charged to a value of VDD. Now the second phase is evaluation, which means I am going to make phi equal to 1. If I make phi equal to 1, this is the phase where you can get the evaluated output for the input value of your Boolean function. Say if you give any value for n1, n2, n3, based upon the input, either the output will be retained at VDD or it will be pulled down to ground based upon this phi, that is phi equal to 1. So that is evaluating the logic, and based upon the input value which has been given to that input, you will get evaluated to 0 or 1. That's why we call this dynamic logic in two different phases, pre-charge and evaluation. Remember the pre-charge, if you consider the clock period, the 0 time period is very short duration, and the evaluation time period is comparatively higher duration, because this short duration of phi equal to 0 is quite enough to charge the output node to VDD. Right. So the beauty is it's not n plus 1, it is n plus 2 number of transistor. It is ratio less. You are not tapping your output via a ratio, because it's either being connected to VDD or being connected to ground. There is no ratio here, right? No static power consumption. That's the beauty of this. You have actually removed the problem that exists with the ratioed logic, right? There is no static power consumption. The noise margin is small, and it requires a clock. These are the some of the difficulties. It requires a clock means it clock again consumes power, right? All this are entering into complications. Okay, how do you evaluate this? This is very clear. In the evaluation, you are going to keep phi equal to 0. Pre-charge the phi equal to pre-charge phi equal to 0, evaluation phi equal to 1, and phi equal to 1, this is my clock. The output either get pulled down, or based upon the input combination, it can also be at the same VDD also. During the pre-charge period, phi equal to 0, the output get charged to a value of VDD. That's what you could see here. The output moves to a value of VDD in the pre-charge. The output get pulled down to ground during the evaluation phase. Now let's see what are the problems associated with dynamic logic. Dynamic logic is good enough, but it also has some of the problem. What is that? See, during the pre-charge period, it makes sure that the output node get connected to CL and it is being charged to VDD. Now you need to remember this capacitor which is being charged, when it find a path for leaking, it start discharging. Why? Say this end, you could see there is nothing but a reverse bias diode will be there. So this is P and this is N and the bulk is P. So it's something like a parasitic diode, and to the parasitic diode it has been connected to VDD, that is output node. So which means this diode has been reverse bias. When a diode is reverse bias, you could get a reverse bias current flowing through that network. That's how you get this. So what happens here is, during pre-charge it has been charged to a value of some higher value. During evaluation, what happens here is it get discharged by or leaked by some amount. So see here, this leakage becomes a problem. Charge leakage becomes one of the major problem. Thereby reliability of the output becomes the question with respect to what you call it as a dynamic logic. And the second problem is charge sharing problem. So whenever you are trying to store some charges, it will always create problem with respect to leakage and the charge sharing. Say suppose you have charged to the charged CL to the value of VDD, and now you have made this MA transistor to be in on. So what will happen? This charge VDD will find a path to share its charges with the nearby capacitor CA. Whereas even the other transistor is switched off, you could see this charge VDD will get shared with the neighboring capacitance. Even the other capacitors are switched off, it is expected to be at VDD, but it won't be at VDD, rather the charge get discharged to the nearby capacitor. This is what the problem here. This is what you call it as a charge sharing problem with the nearby capacitance. Because you have kept this in 1, A to be in 1, B to be at 0. If you keep this set, actually what should happen? The output should be at 1, but naturally it will not be at 1. The reason is this MOSFET is in on, so you could find a path from this end to charge this capacitor. So some amount of VDD would have been reduced. VDD minus some delta voltage would have been reduced from this VDD. Right. So how to solve this problem? Like there are many papers which spoke about solving this, like pre-charge of internal nodes. So if you yourself pre-charge all the internal node, that will avoid charge sharing problem. This was one of the suggestions given, and you can also use static bleeder type of network in order to avoid this charge distribution. And one more problem is clock feed through, right? Whenever the clock makes a quick change at your output, you could see there exists a capacitance between gate and the drain. Then this capacitance charges and discharge. This will also create a problem, or charge sharing with respect to this CL will also take place. So this is again, all this problem comes with dynamic for the simple reason, because in dynamic we are trying to store the charges at the output. That's what you could see, the output voltages get down and the internal nodes get charged to a value. So how to sort out this issue, right? So people come up with the different techniques of charge sharing, addressing the charge sharing, leakage problem. Beyond this, you also have one more problem with the dynamic, that is cascading problem. Cascading in the sense connecting one dynamic logic with the next dynamic logic. What's going to happen? Say if I connect two inverters which has been implemented in dynamic logic, then you come across one more issue or one more problem, what do you call it as, the output of the second stage get pulled down. Let's see how it happens. Say suppose in the pre-charge, definitely the phi equal to 0, the pre-charge output 1 and the output 2 both will be at VDD, for the simple reason phi is going to be at 0 in the pre-charge. When it comes to evaluation, when you give in equal to 1, what is expected during evaluation? Phi equal to 1, and input is also equal to 1, phi equal to 1, input is also equal to 1, then this output will be pulled down to ground and it should be made as 0. So till the time this output come down, you could see here this phi is also 1. So what is going to happen? Till it goes less than that of Vt, it is switching on this MOSFET also. Since this switch on this MOSFET, it's again dragging the output of the second stage to the ground. So what you could notice, this take place till your output voltage goes less than that of Vt. So what you could see here, the first output node goes to ground. In the second, you could see till the point where it get less than that of Vt, your voltage get reduced by a value of delta V for the second. So it's like a domino effect. That means you push one, the other one push the other. Like it is dragging this power, it will drag here, it will drag here. Subsequently, it keeps on dragging the next stages, pulling down the voltage of the subsequent stages. So we find it very difficult to cascade the dynamic logic. So how to solve this issue? So a couple of solutions have been framed, what you call it as a domino effect or domino logic. This domino logic is very simple. You create a dynamic logic, and at the end of dynamic logic, you include one static inverter logic. So thereby what happens? This propagation of the output to the next stage may not trigger the output pulling down. You have one inverter after every dynamic logic. So one dynamic logic, one static inverter, these two combined together, it is called as the domino. Now this will not pull down the voltage of the second stage, because during that time this is going to be 0. So definitely that will not pull down the output of the second stage. So in that way, the problem of cascading can be resolved. So this style is called as the domino logic style. One more, you can also think about having this NP combination. If you make this in pull down network, the next stage you make it in pull up network. So naturally, even if this output is 1, that will not trigger the second stage, which is in PMOS. So thereby you can avoid the problem of cascading. So to avoid the cascading problem, you can go with the NP CMOS, or you can even go with this domino logic. So this is what, so we have seen different types of logic style, their pros and cons. I hope this would help you.